Today is our introduction into magnetism. Our focus with magnetism is going to be what is a magnet, how does it work, what things are magnetic, and how do magnets, magnetic fields, interact with electrical current and electric fields, which we've been spending quite a bit of time on in this unit. So what makes something magnetic? Simply moving charges. So everything that we've been doing when it comes to electrical circuits to this point is all about charge that's moving. Okay, whether it's through a wire, through something with some amount of resistance, whatever it may be, even going back to Unit 5 with static charges, friction, contact, induction, etc. Magnetic things are made by moving charges. So for us, when we look at this, we're talking about electrons and their movement can actually make something magnetic. Charges, whether positive or negative, that are moving with any kind of velocity. As we go through this, you'll see magnetic field lines, very similar to electric field lines, drawn showing the direction that a positive charge would go, like our electric fields. Positive and a north pole are going to be very similar as we go through this. So the second thing, what makes an object magnetic? It has to do with what we call domains. Objects that have magnetic material within them have what we call domains, and these are areas where there are essentially miniature magnets within them, and these domains, in some material, they're lined up really well, others not so much. Others, there's no domains at all. As you can see on the far left, there are these arrows pointing in all kinds of random directions. This would be stuff that is not considered to be magnetic. Magnetic materials, there are three major, or the most common substances that are magnetic: iron, cobalt, and nickel. And other lesser materials can be magnetic, but these are the three major ones. And when you actually get something that is a magnet itself with poles, all those domains are lined up. You can make something that is simply magnetic into a magnet itself by getting the domains aligned. Things that are not magnetic, non-magnetic materials, you can temporarily align these to get it to act magnetic, but it's always something that is very temporary. So, as I mentioned before, magnets have poles, and we identify them as a north pole and a south pole. If you take a large bar magnet and you were to split it in half, now you have two magnets, each with a north pole and a south pole. It will be a weaker, both sides will be weaker than the original larger one, and if you split those, you're going to get still smaller. If you continue to split them down, you're always going to get a magnet with a north and a south every single time. Now, where these terms are very familiar to us happen on planet Earth, and we'll look at that here in a moment. The last major thing when it comes to the basics of magnetism are magnetic fields. Just like with electricity, we have electric fields. We always drew electric field lines in the direction that a positive test charge would feel the force. So if you were to draw out the electric field lines between this positive and negative charge, the lines are always going to point in the direction of the negative charge. And even ones that are going towards, nearest to the negative, they're all going to move in that direction. From positive, they're always going to move away. From the positive, if there is a negative in the vicinity, they're going to move towards that, so on and so forth. Magnetic field lines, very similar. They're lines that are drawn in the direction a north pole would feel a force. So very, very similar is from a north pole, you're going to feel repulsion. If you bring a north pole near a north pole, if you actually did this with two bar magnets, you would physically feel that repulsive force. But because the north and south poles are connected on a bar magnet, where they're going to look a little different is they'll actually connect like this. and we can make a whole bunch of these, again largely dependent on the strength of the magnet. The stronger the magnet, the more lines. Just like an electric field, stronger the electric field, the higher concentration of field lines that we would draw. But that is exactly what would be happening here, very much like electric fields with the direction of a positive. In place of it, a north pole. Finally, in terms of basics, as we mentioned, the North Pole and South Pole names or terms, our planet is one gigantic magnet. And now pay close attention here to how this bar magnet is set up inside of the planet. You notice that the South Pole is pointed towards what we consider to be north, and the North Pole is pointed in the direction that we consider to be south. That is accurate. Our compasses, if you take a look at the colors, and you can see the red and the white lines, our compasses show us the direction that north happens to be. What it's actually showing you is what a North Pole is attracted to, and it's attracted to a South Pole. So when we say a geographic pole versus a magnetic pole, those are opposites. And here on planet Earth, they're almost perfectly aligned, but basically our planet serves as a gigantic magnet. And towards the end of the lesson today, you're going to be watching this video about a magnetic storm, which really gets at what our electromagnetic field can actually do for us here on Earth in terms of protection from all kinds of stuff from out in space.